At Longbridge, where Austin cars are made, a scientifically equipped army of inspectors guards against all error. They check every piece of work to the finest limits. Using delicate and costly instruments, they split the inch into its 10,000th part and even less to ensure that every component is true to specification. Watch them while on duty. Checking all the gearbox dimensions is an onerous duty in itself. There are more than 100 dimensions to be verified in this one component alone. The end face of the gearbox must be accurate. The size, alignment, and spacing of bearing housings must be exact if a silent transmission is to be ensured. The selector mechanism must also be accurately allowed for to give an easy gear change. So the ceremony proceeds, while every important dimension is being verified. Now let us examine the simple principle of these go and not go gauges. Go and not go. It is a way of accurately deciding whether a dimension is within the permissible limits. The go end of the gauge represents the lower limit, only 1.5 thousandths of an inch smaller than the not go higher limit. The piston rings demand a very high degree of accuracy, and so a light test verifies the circularity of each ring. If the ring totally obscures the band of light, it can be passed for grading. Between 20 and 30,000 rings pass this test in a normal week. The rings are also graded within a maximum variation of 0.5 thousandth of an inch. Each ring is pushed along a taper bore until its gap closes, and its position in the bore then indicates the piston to which it can be fitted. But pistons, as well as being graded for size, are carefully weighed and then selected by weight as well as by dimension for every engine. Balance and dimensional match are both essential and are both ensured. No error can be risked, not even distortion by punching, so the pistons are electrically numbered for identification. But all this meticulous care would be of no avail if the cylinder bores were not quite as carefully checked for size and accuracy by a pneumatic micrometer. Look at the gauge tube behind the cylinder block. The column of liquid indicates the size of each bore as felt by an air jet in the gauging plug. The escape of air from this jet, as permitted by the clearance in the bore, determines the pressure above the column of liquid, which adjusts its level accordingly. The liquid is so sensitive to variations of dimension that the thickness of a film of oil can be readily detected. Watch. The thickness of the oil film, less than 1/1000th of an inch, is multiplied 9,000 times in the reading of the liquid column. Even the cylinder heads are scrupulously tested. The machined combustion chambers are filled with liquid so that their volume can be verified. Each must be accurate to within 1/2 cubic centimeter. But smooth running also depends on perfect balance of the rotating parts. The machined crankshaft is revolved and each end balanced separately by the adjustment of counterweights until the highly sensitive needle ceases to vibrate. The setting of the weights then reveals the unbalance, and the inspector can determine the unwanted weight and indicate where it must be removed to render the balance correct. There are other moving parts, the clutch for instance, for which the same procedure is adopted, using a highly sensitive machine to secure a perfect balance. Weights are adjusted to counterbalance the unwanted weight, which once measured and located can be removed by drilling. A final test then shows the balance to be perfect. The hardness of the wearing parts has also to be verified. Small parts, such as tappets, are tested for hardness one by one by a diamond point, and not a tappet passes unchecked. And so the culmination of all the care and precise workmanship devoted to the engine parts is subjected to the final and crucial test. The assembled engine drives the dynamometer, which measures its power output. After running several hours under varying loads, just to free and stretch its limbs, its power is recorded on the dial. A 10-horsepower engine must give over 20 horsepower at its maximum working speed, or the inspector will reject it. Now suppose we trace precision back to its very fountainhead, and for our purpose take as example that intricate component, the crown wheel of the final drive. Its teeth must be so accurately spaced that less than 1/1000th of an inch in variation is permissible. But the fingers of this delicate instrument are sensitive to 1/10th of this amount, and they register on the dial the extreme accuracy of this Austin crown wheel. This is because the tool which cut the teeth was equally exact, as verified by a profile gauge, against which each separate cutter is scrupulously set. Accurate components can only be produced by accurate tools. Let us go one step further back. Can we be sure of the accuracy of the profile gauge? Here is the optical test in which accuracy is rendered visible. Through the glass table on which the gauge is fixed, a beam of light is projected upward. With the micrometer adjustment, the projected profile of the gauge, many times enlarged, is moved into register with the master outline, and even the slightest error can be seen. A beam of light is also employed to test the various gauges we have seen in use. The light beam measuring machine is set at 0 by the master gauge. Each gauge can then be compared with the standard of precision by the extent to which it deflects the beam of light. So sensitive is this source of Austin accuracy that the expansion of a steel bar arising from the heat of the hand is instantly recorded. The length of the bar has been increased by 1/10,000th of an inch. And so the standard of dimensional precision is unfailingly maintained. Accuracy assures that dependability which you expect and obtain from your Austin.